By the end of today, I think I posted, if it hasn't been posted now, I will post an assignment one. You'll have a full week to take care of it and stuff like that. So you don't have to worry about it. But the main focus of assignment one is just to get you started. There's a few basic questions about data types and a couple of how to interpret a graph and stuff like that. But the real key is there's a couple of questions at the end there where it asks you to do a really simple Excel statistical calculation and a really simple SPSS calculation, and to upload your results onto Blackboard. And I do that the first session because I want to make sure that you guys get SPSS and Excel installed on your computers or have a way to work with it and so on and so forth, so you don't wind up falling behind because you don't have the mechanism. And if I see that you're struggling with assignment one, that you're not able to do it, I know to ask you about it and see if you're having problems getting access to the software and so on and so forth. So that's a real impetus behind assignment one, is really get things rolling. Okay, so let's talk about this. Now, I'm going to give you a little bit of my history in statistics, which is I'm not a statistician. I'm not a biostatistician by trade. My profession is environmental occupational health science. That's my degree. But I have a long history in engineering. I went to Brooklyn Poly as an undergraduate a million years ago. My first statistics course I took in I don't know if it was 67 or 68. So that puts that into perspective about how long ago I was taking statistics. When I took statistics, you did it with a piece of pencil and a really basic kind of calculator. I'll give you an idea what that looks like. Okay, that's what I used when I took statistics. It's a mechanical calculator. It's actually been modified to use an electric motor, and you actually type in numbers into that and hit a button, add, subtract, and so on and so forth. The one that I used, really sophisticated, was able to do squares and roots as well, which is kind of like a interesting thing to be able to do. I think squares at least. Now I think about it, maybe not roots, but squares is what you really needed for statistical calculations, as far as I'm concerned. So we've come a long way from that. Okay, and that's another thing, slide rules inside. And you guys ever see a slide rule in real life? You have. You have a father that's an engineer or something like that? Is that really?
He's not an engineer.
Oh no, why would he have one if he's not an engineer?
Got a lot of things he doesn't
need. I like that. That's good. Okay, so at any rate, so fortunately, in the early 70s, in the late 60s, early 70s, we started to see the advent of electronic computing, mainly to do basic mathematical operations. They got more sophisticated as time went on. This is a very early desktop model. Eventually, it was displaced by handheld models, HP 10, TI 51 or something like that, Texas Instrument and so on. And they were the earliest of these calculators. So it really changed what we were doing quite a bit. So when I was taking computer science in college in those days, there were no such things as personal computers. There were mainframe computers. There were rooms, air-conditioned rooms that had these gigantic machines in them that probably did not have the computing power of what your laptop has now. But they were enormous pieces of equipment. And we weren't allowed to interact with them directly. We wrote programs on in various languages. I learned something called Fortran and COBOL and so on and so forth. We wrote computer programs on using these languages. We typed the each line of the program on cards, on these things called Hollerith cards. And if I can come up with one, I'll show you one at some point. We typed them in, and each card represented a line of code. So you would have a deck, like a deck of cards. They're about that big. I'm holding up my hands about 3 inches high and about 8 inches across. There were cards about that big, a little slant on one side so you know which direction to hold them in. And each one of them represented a line of code that was interpreted by the computer from holes that were punched in the card, called Hollerith cards. So we would hand them into a computer room. Someone during the middle of the night would run them through read them into the computer, run the programs, give us a printout. We would pick up our cards with the printout at the end of that time. So it was really difficult and cumbersome to use a computer as a student back in those days, or even as a researcher, because you had to go through someone that would be the intermediary for you to actually work with the computer. So we eventually wound up with personal computers in the starting in the late 70s, early 80s, and that really changed the approachability of computers. So you had people with statisticians, engineers that were dropping their pens and pencils and their electronic calculator and moving over to computers. One of the things that we used to do in order to do calculations is we actually basically use ledger paper in order to do calculations. Ledger paper, just basically a big piece of paper, columns and rows. So if you're an accountant, you would have debits on one side, credits on the other. At the bottom of the page, you would add up all your credits, add up all your debits. You would move them over to the next page. And then as you had transactions, they would keep going and so on and so forth. If you're an engineer, you would do your calculations that way, your load calculations, your stress calculations, just that way as well. And then when you got to the very bottom, you'd have an answer of how many pounds per square inch or whatever you were calculating that was the result of all that. Problem with this is that if you made a mistake anywhere in the process of doing those calculations, you got to go back and start all over again, right? Because you couldn't just erase that number. You had to go back and redo all those calculations. So on the right side of this screen, what you're seeing is the corollary of that ledger that we used to work with, that ruled paper that we used to work with, and that's on a computer screen. It's what we would call nowadays a spreadsheet program, right? And that spreadsheet program was literally displaced the idea of doing this all on paper. And the first successful spreadsheet program on microcomputers was a program called VisiCalc. These are the two guys at the bottom that developed the program. They worked at the Harvard Business School. And basically, they were using this for financial calculations. And they decided, well, we're working on these ledger sheets. Why can't I just translate this onto a computer screen and then be able to do these calculations? And then they came up with the idea, well, let's actually embed the operations, the calculations, into each cell. But the thing that really made this useful is that if you had various calculations where one was dependent on the next and the next and the next and the next, if you made a mistake in the first one, it affected everything that went beyond that. But now with this electronic version of this ledger, if you corrected that mistake, it would automatically correct all the mistakes down the line as well. So it made this whole thing enormously powerful. These guys, there's a video that was on YouTube. It got pulled. It was part of a PBS special on the early people in the microcomputer revolution. But they have these guys talking about when they first came out with this program, they would go to these computer shows and people in accounting and business would literally would be begging them to take their credit cards and their cash to buy this program. It only ran on the Apple II, by the way, which is one of the reasons why the Apple II was such a popular computer very early on with businesses, what they called back in those days, a killer application. People bought the computer to run this application. That's the impact that this has. Now, so that's just progressed. And it's progressed to the point where, okay, let me see if I can't get this to advance. Okay, yeah, there you go, computer ledger. Okay, so you can embed formulas and stuff like that, but it's progressed to the programs that we see now, like Excel. Excel is a spreadsheet, but it's not just used for business. It's used for accounting. It's used for calculating business loans. It's home loans. It's used for exercise programs. It's used for statistics. It's used for all sorts of home budgeting and so on and so forth. It has a million different uses. It's kind of a horizontal program. One program has a lot of different uses. Okay, that's very utilitarian for us because we can use it for statistics, but we can also use it for a lot of other things as well. Problem is when you ever heard the expression, I may be dating myself, jack of all trades but master of none. You've heard that expression, right? So it's kind of that kind of piece of software. While it's enormously useful for a lot of different tasks, it's not always the best choice for specific uses. There are programs that are vertical programs. They're designed for a single use. The one we're going to be using this semester in order to do our statistical calculations for the most part is called SPSS, Statistical Program for the Social Sciences. That's its original name. It was bought up by IBM about 8 or 10 years ago, so now it's IBM SPSS. So that's what we're going to be working with. Okay, now then the other thing that we may come across a little bit is programs called database programs. there are programs that are specifically designed for handling huge amounts of data so that you can organize it, you can search it well, and so on and so forth. The simplest of these might be like your contact list on your computer, right? That's a database program. It has name, address, phone number, zip code, so on and so forth. And you can search through it for a name. You can alphabetize it, and so on and so forth. So more sophisticated versions of these database programs are used for organizing and handling massive amounts of data. So there's a whole bunch of them. You've heard of Oracle, for instance, is one of the companies that has basically a database program, and there's a legion of others as well. Okay, so that's one, and then there's our SPSS. We're going to open that up later on, but you can get a glimpse of it here, and it looks kind of like a spreadsheet program. Don't let that fool you, though. It doesn't work anything like a spreadsheet program. However, one of the reasons we use SPSS as opposed to other statistical programs like R, which is a free open source program, which is becoming very popular with professional statisticians because there's a lot of packages that you can add on to it to do special statistical analyses, and it has a lot of support, technical support, free technical support. One of the reasons we go with this instead is because it's very approachable. It looks like a spreadsheet. Most of the work that you can do on here is menu driven, so you don't have to learn a language kind of in order to use this. Where with R, you might have to do a little bit more training in that software. If you're interested in working with R, we don't support it, but you can go ahead and do it if you want to take a course online or something like that. You can go ahead and you can do any of your assignments or homeworks and get the output using R and use that instead. I have no issue with that. It's just a matter of you knowing how to do it. Okay, but it's useful also to learn how to use SPSS because that's one more item on your resume. A lot of corporations, a lot of research facilities use SPSS. Department of Health uses a similar program called SAS, and there's others as well. Okay, so the nature of this is that what we're dealing with when we're dealing with this information, we describe the bits of this information as variables. Okay, and we have a number of different variables that we work with. There's a way that we classify them into a number of different types of variables. And this is important to us. The reason why this is the first thing that we're regurgitating here, this idea of data types or variable types, is because the type of variable, the type of information that we're dealing with impacts how we're going to analyze it, what kind of tests we're going to use, how we're going to organize the data, how we're going to display it graphically, and so on and so forth. Okay, so what kind of data types are we working with? I'm going to tell you basically there's really three basic forms of data that we're going to work with. There's kind of subgroups of each one of these things. So you're going to hear me use a lot of different names for these data types, but there's three basic kinds that you should really focus on for a couple of reasons. One is because all the others are kind of like a version of those three basic kinds. And the other is that SPSS only asks you which of these three kinds is it. Doesn't ask you specifically, is it, we'll talk about it in a second, is it discrete, or is it, in other words, integer, or is it a scalar numerical? Just wants to know it's numerical, right? And so on and so forth. So these three basic types are what we're interested in. That is nominal, or sometimes also called categorical. Anything that's a name, right? Anything that describes something in kind of in a name. So, for instance, a variable called hair color might be red, blonde, brunette, so on and so forth. Might have each of those different values, right? But they're names. Each value is a name, right? So next is numerical information. Okay, and that could be like blood pressure, right? 80 milligrams of mercury. Could be atmospheric pressure, 17.4 psi. Could be blood lead levels for children, 4 micrograms per deciliter, and so on. Anything expressed as a number on a scale. Could be a scale of 0 to 1,000,000, could be a scale of 10 to 50. Anything that's expressed as a number on a scale that makes some sort of sense in terms of being a rational scale. So there's another kind of data, which is kind of categorical data also, which is called ordinal. And that is names or numbers that don't really represent something strictly on a scale, but imply some sort of order. So, for instance, if we were graded as fair, good, or excellent, right? We have three values. Grade, the variable name is grade, and the values you might have is poor, fair, good, or excellent, right? Well, those are words, right? So it's nominal data, it's nominal information. That's a word, good. That's a word, fair, and so on and so forth. That's nominal or categorical data, but they have some relative meaning. For instance, fair is better than poor, good is better than fair, excellent is better than good, and so on. However, even though they have some kind of order, we don't know that that the difference between fair and good is the same as the difference between good and excellent. Maybe one's a bigger gap than the other. A pain scale, for instance. What is that? That's called a SAFR index or something like that, right? Pain scale. You know, how much pain are you feeling right now? And you say 0 to 10. Yes, but patient 0 to 10. And the patient says to you 8, right? Well, that's an example of ordinal data, because your 8 might be different than your 8, right? May not be the same thing, but we know that if you say, well, how are you feeling now after we gave you a couple of aspirin? Oh, now it's a 4. We know it's less painful. You're in less pain, but we can't really quantify that as a solid number for everybody across the board. And also, we can't say for sure that if you went down, the difference between 4 and 8 is the same thing as the difference between 4 and 0. Right? Maybe, or the difference between 5 and 6 is the same thing as the difference between a pain level of 8 and 9. Right? It's not something we can put them in order, but we really can't quantify them besides that. So, ordinal, categorical or nominal, and numerical. Okay, within each group, nominal, you can have integers, right, where the value is an integer. How many siblings do you have? Right, that's always going to be an integer. You're not going to have half a sibling, right? So, well, I have 2 brothers and 3 sisters. I have 5 siblings. That's numerical data. It happens to be an integer form of data, and we often call that discrete data. Okay, how many cups of coffee did you have? How many whole cups of coffee did you have today? You might say, well, I had 3 cups, or I had 2 cups, right? Well, that's discrete nominal data. Effectively, when we start to work with this, it's not going to make that much different, but it's going to come up occasionally as we move on. Okay, I wouldn't get too crazy about it. We might have numerical data if it's the kind of normal kind of numerical data I was talking about. Sometimes we call it continuous data. Let's see. Okay, in nominal data, right? We could have hair color, red, green, yellow, blue, whatever hair color you might have, right? But on the other hand, very frequently we have situations where we're dealing with nominal data that has only 2 values. For instance, a person's sick or they're not sick. They were exposed or they weren't exposed. They took a drug or they didn't take a drug. They took a drug or a placebo. Only has 2 values, right? They have diabetes or they don't have diabetes, right? That's called binomial data. So it's nominal data, but only has 2 values. Gender, male or female, right? Is a form of binary data. So still categorical and nominal, but it's a special form of it. Okay, so let's move on from there. Again, SPSS usually only deals with those 3 main forms. When in this class, we are going to be interested in information about populations. Very often, we'll be taking samples of people, surveys, and so on and so forth. Basically, it's a sample of people. But we're not really interested in samples, right? We're really interested in populations. We want to know what the average blood pressure is for all males between 40 and 50 in New York City. We want to know what's the average blood lead level in children and 5-year-old children in New York City school system. We want to know what the average for all of them is, right? Problem is it can be very expensive, tedious, impractical to gather information from all, for all of the students in the school system. So we're limited to only being able to measure a small part of that population. So what we do instead is we take random samples. We attempt to randomly sample enough people from that population that our sample then becomes representative of the whole population. So for instance, if I'm interested in knowing what the average blood lead level for children, 5-year-old children in the New York City school system, it's a bad example because they actually do test all children, I think, at a certain age, right, in the school system, like 4 or 5 years old. They do. Well, I'm going to talk about that in a second. They do. If we couldn't afford to test all the children, we might try and take a random sample, so many from each borough and so on and so forth, randomly sampled based on some listing that we have of the names of all the children and so on. We might ask to get a sample from each one of those children, maybe a few hundred children, for instance, instead of a million children. And when we calculate an average for that sample, our thinking is that if we have a big enough sample, that the average for that sample is probably pretty close to what the average for the population is, right? So we can go home now because that's statistics, right? That's basically what we're doing here, right? So what we're really interested in is the population, right? We're really not interested in the result from our sample. We're only using that sample to get information about the population or to be able to understand the population. Okay, so there's a few things that we're going to work with here. We're going to differentiate between information we know about a population and information that we know about a sample. Okay, so for starters, anytime we talk about information about a population, that's called a parameter. So the average for a population is called mu, right? The standard deviation for a population, you don't have to worry about that. That's a measure of spread. We'll get to that eventually. That's a measure of the spread, like the lowest number to the highest number. How spread out are the values in the population? That's called standard deviation. We use the Greek letter sigma instead. And and then there's other things that we're going to be using calculations for. Let's worry about those two for starters. In statistics, we use English letters. X represents a value. In fact, usually what we do is put a bar across the top of it. We call it X bar. That represents the average for a sample. And SD, or standard deviation, represents the spread for the sample, not the population. Again, the thing is, though, we get a good random sample, and it's a big enough sample. Our assumption is that our statistics will help us estimate what the population value is. Okay, then another big part of at least in the beginning for us now, and usually going forward, big part of what we're going to be doing is we're going to be understanding how to summarize and organize data so that we can communicate information about populations and about samples. Okay, it's one of the things we might do is we might organize it into tables, and from those tables, for instance, here we're talking about there's population data on the left. I think there's mortality data on the right, and so on and so forth. So we've organized that into tables to make it more understandable. Obviously, it's hard to read this. I'm getting a headache just looking at these tables, right? Very frequently, you'll try to organize it into graphical information. As they say, a picture is worth 1,000 words, right? So, for instance, here's our hair color. This obviously I stole from some British website, right? COLOUR, right? So this is a bar chart, right? So we can tell in this sample there were 2 students that had red hair, there were 4 students that had blonde hair, and so on and so forth. I can see that information at a glance. I could have organized the data that we saw here that way also, so that it was much more understandable. The other kind of bar charts: a whiskey bar chart, candy bar chart, and of course a sushi bar chart. That's it. That's my only joke in statistics. We'll get another one from me for the rest of the semester. Now, that's fine for categorical data, right? Because this I'm organizing categorical data. How many redheads were there? How many people with brunette hair were there? How many people with black hair were there? Right? So that bar chart is very suitable for nominal or categorical data. Here's our first place where we see, depending on the type of data it is, how things start to diverge. If I have numerical data, like here, I'm measuring heights, right? Well, a person's height is not nominal data, right? You could, unless you called it short, tall, and taller, or something like that, not nominal data. It's an actual number. So, for instance, these I guess are in centimeters, right? So if you're between 135.5 and 149.5, you would be in the first yellow bar. If you're between 149 and 159 centimeters, you would be in the green bar, and so on and so forth. The idea here is that you're going to be in one of those bars. In other words, if you flip over, in other words, if we could have redrawn this, so we had a bar between 135 and 140, 140 and 145. We could have drawn this any way we wanted. But the number of people that would have been in there would have been the height of the bar would have represented the number of people that are in that range. But they all would have wound up in one of these bars. So notice something different about this. What's the most distinctive thing you see about the difference between this and this? They're touching, no space between them. That's indicative of the fact that in this one, that they're not really related to each other. You're either red or black hair or whatever. In this one, you cross over from one to the other. There's no space in between. If there was a space in between, it would be there to indicate that there's nobody in that range, right? That may happen occasionally, right? So that's called a histogram. That's the difference between a histogram, which you use for numerical data, and a bar chart, which you use for categorical data. Okay, bar chart or histogram? Bar chart, right? Bar chart or histogram? Histogram, right? Okay, now, one of the other types, there's other kinds of graphical data that we put together. Okay, this, for instance, is something that's very useful to us in statistics called a box plot. And in a box plot, I'm going to refer to this one on the right first. First of all, let me see if Angela had any input here. Angela, you still awake? They're yawning over here, I can tell you that. I'm going to wait for a response. Yeah, okay, good.
I'm here. I was in the bathroom.
I'm going to leave your microphone turned on. I didn't realize that I forgotten to mute it, but I'm going to leave it turned on since you don't have any domestic violence going on in the background, no dogs barking and stuff like that. So,
Right.
Okay, good. So at any rate, so this.
Professor, I think you have two Angelas. This is Angela Chiwanuka.
Oh, I'm sorry, Angela. Okay, good. What did I say?
You asked if Angela was on.
Oh yeah, yeah, exactly. I appreciate that. I'm going to leave you. Normally, I would mute your microphone, Angela, so that we wouldn't get background noise from your end or echo and stuff like that. So when there's more people on, you may find that I mute your microphone, and the only way to communicate with me is to type into the chat box. But I'm going to leave your mic on.
I understand.
I'm going to leave it on for now since we're not having an issue with it. Okay. So anytime you want, you can interrupt me if you have a question. So anyway, so this box plot, this on the right hand side, this single on the right hand side, this box plot, single box plot here. The way we interpret this is that these two horizontal thin lines here are called feathers. The lower one is the lowest value in the sample. So this is a sample of some information. Actually, it's diameters of trees. These are red maple trees. One is when they're in part sun, the other one when they're in full sun, right? And here you have sugar maples in the second group and black maples in the third group. So right now we're just looking at red maples that grow in bright sunlight. So I'm looking at this box plot on the right, and so I can tell that of the trees that were sampled, the smallest diameter was about 12 inches. The biggest diameter was about 18 inches, right? So the other thing I can tell is this line in the middle represents the median, the middle value, not the average. As it happens with box plots, we display the median value as this line in the middle. Okay, this red box that's here represents the middle 50%. The bottom of it is the 25th percentile. The top of it is the 75th percentile. The median is the 50th percentile. Half of them are below that, half of them are above, right? So basically what we have from here to here, we have the first quartile, From here to here, we have the second quartile. From here to here, we have the third quartile, 25%. And from here to here, we have the fourth quartile. So the 25%, the 25, the largest, 25% largest trees are in this top part here. So that's the way we use this. The red box in general, from the 25th percentile to 75th, we call the interquartile range, the middle 50% of the values. It's an easy way to describe how a sample is distributed. So we can look at this picture and we can see, smallest to biggest, how much of them are, where is the middle, the 50th percentile, half of the trees, where is the 75th and 25th percentile, middle 50%, and so on. What do you think this red dot at the top is? Bingo, an outlier. I meant to ask you guys if you've taken statistics before. Okay, so anyway, so that's an outlier, right? So in this particular SPSS has a built-in formula for determining whether a value is an outlier. You can manipulate that formula. Basically, what I think it does is it takes a 1.5 times the difference between the 75th percentile and the high and the 20 and the 50th or something like that, whatever it is, has a particular way of calculating it. And it will identify some outliers like this automatically. You then have to make a decision. Is that appropriate for your data? In other words, should you include that in your analysis? Should you exclude it in your, you'd have to really evaluate why it's an outlier and where it came from, what it represents. So that's always going to be an issue for us, but we'll deal with that later on. But that's how we interpret this box plot. The real value in this box plot is when we do side-by-side box plots. For instance, now we can see red maples are smaller trees than sugar maples are. In general, look at the median size for sugar maples and median size for red maples. And I can also tell that, for instance, and when they grow in full sunlight, they don't grow as well as part sun. I don't know why for red maples. However, that's not true for sugar maples, and it's not true for black maples. And look at this. This is very interesting. Look where the median is here, the 50th percentile for sugar maples, all the way up here. What does that tell you? That tells you that 50% of the trunk diameters are between 28 and 36 inches. And then the other 50%, lower 50%, are between 30 and about 12 inches. This distribution is skewed. There's a lot of big trees, not many small trees. Right? But excuse me, there are a lot of big trees, but they're within a small range. But the smaller trees are distributed across a much wider range. So there are some really small trees that, if we took the average instead of the median, would pull that down, the middle of this down. The fact that the median is up here means that there's the same number of trees above it as below it, but the fact that you have some very small trees means that the average is going to be lower than the median is, because the average is going to be pulled down by these extremely small values. Okay, so just something to think about. We'll get to that in a little while. Okay, the other way we frequently display data is scatter plots. In this case, we're associating two numerical data. One is a husband's age with a wife's age. And we can see that each dot represents an individual in a sample. So, for instance, this dot here represents a 53-year-old male whose wife looks like 52 years old, right? So, and so on and so forth. And we can see there's a pattern here. That's called a correlation. We're going to be working with that later on in the semester. I want to show you a quick video on displaying data, but I'm going to come back to that in a second. Okay, matter of fact, we're going to do some hands-on work with Excel and XPSS. We're not going to work on R because, again, like I said, we don't support that directly here. But who knows? Maybe we'll play around with it a little bit if we get a little bit of time as the semester goes on. So I want to play this video for you. Now, Angela, I think it's possible. I have a link to this on Blackboard. This is a TED video, or the first 6 or 7 minutes of a TED video, by Dr. Hans Rosling. Let me see if I can't find it here on YouTube. I'm going to play this here. You may find it easier to just play it on your computer instead of watch it with my broadcast. Yeah, it depends on how good our connection is. Hans Rosling. Okay, now this never.
To fly a rocket ship, you need to be an optimist.
Why not have an and?
No astronaut launches for space with their fingers crossed. That's not how.
I've started to get interested in that. Okay, now I need to turn up the sound here and see if I can get this to work here. Okay, why don't I? Oh, it's my screen I'm seeing here. So what do I have to do here? Let me think about this. Maybe I have to escape. That's it. Escape. Okay. Let's see if this works. That's not sign over there. What I'm going to do, I am going to open it on here. Use this. Let's see. What do I do here? I want to do that. I don't want to sign in. I don't want to try red. Boy, it's work getting around a little commercial here. It's a search.
So I just created this dope website with Wix. Let me show you how I did it. First up, go to Wix.
Okay, I'm gonna let this run. I'm gonna be back here by the time it's done. I'm gonna put money in the meter. I'll be right back. That's too loud.
About 10 years ago, I took on the task to teach global development to Swedish undergraduate students. That was after having spent about 20 years together with African institutions studying hunger in Africa. I was sort of expected to know a little about the world. And I started in our medical university, Karolinska Institute, an undergraduate course called Global Health. But when you get that opportunity, you get a little nervous. I thought, these students coming to us actually have the highest grade you can get in Swedish college system. So I thought maybe they know everything I'm going to teach them about. So I did a pre-test when they came. And one of the questions from which I learned a lot was this one. Which country has the highest child mortality of these 5 pairs? And I put them together so that in each pair of country, one has twice the child mortality of the other. And this means that it's much bigger the difference than the uncertainty of the data. I won't put you at a test here, but it's Turkey, which is highest there, Poland, Russia, Pakistan, and South Africa. And these were the results of the Swedish students. I did it so I got a confidence interval, which was pretty narrow, and I got happy, of course, at 1.8 right answer out of 5 possible. That means that there was a place for a professor of international health and for my course. But one night, late night, when I was compiling the report, I really realized my discovery. I have shown that Swedish top students know statistically significantly less about the world than the chimpanzees. Because the chimpanzee would score half right. If I gave them 2 bananas with Sri Lanka and Turkey, they would be right half of the cases. But the students are not there. The problem for me was not ignorance, it was preconceived ideas. I did also an unethical study of the professors of the Karolinska Institute that hands out the Nobel Prize in medicine, and they are on par with the chimpanzee there. So this is where I realized that there was really a need to communicate, because the data of what's happening in the world and the child health of every country is very well aware. So we did this software which displays it like this. Every bubble here is a country. This country over here is China. And this is India. The size of the bubble is the population. And on this axis here, I put fertility rate. Because my students, what they said when they looked upon the world, and I asked them, what do you really think about the world? Well, I first discovered that the textbook was Tintin mainly. And they said the world is still we and them. And we is Western world, and them is third world. And what do you mean with Western world? I said, well, that's long life in small family. And third world is short life in large family. So this is what I could display here. I put fertility rate here, number of children per woman, 1, 2, 3, 4, up to about 8 children per woman. We have very good data since 1962, 1960 about, on the size of families in all countries. The error margin is narrow. Here I put life expectancy at birth, from 30 years in some countries up to about 70 years. And 1962, there was really a group of countries here that was industrialized countries, and they had small families and long lives. And these were the developing countries. They had large families and they had relatively short lives. Now, what has happened since 1962? We want to see the change. Are the students right? It's still 2 types of countries? Or have these developing countries got smaller families and they live here? Or have they got longer lives and live up there? Let's see, we stop the world. And this is all UN statistics that has been available. Here we go. Can you see there? It's China. They're moving against better health. They're improving there. All the green Latin American countries, they are moving towards smaller families. The yellow ones here are the Arabic countries, and they get larger families, but longer life, but not larger families. The Africans are the green down here. They still remain here. This is India. Indonesia is moving on pretty fast. And in the 80s here, you had Bangladesh still among the African countries there, but now Bangladesh, it's a miracle that happens in the 80s. The imams start to promote family planning, and they move up into that corner. And in 90s, we have the terrible HIV epidemic that takes down the life expectancy of the African countries, and all the rest of the world moves up into the corner where we have long lives and small family, and we have a completely new world. Let me make a comparison directly between United States of America and Vietnam, 1964. America had small families and long life. Vietnam had large families and short lives. And this is what happens. The data during the war indicate that even with all the death, there was an improvement of life expectancy. By the end of the year, the family planning started in Vietnam, and they went for smaller families. And the United States up there is getting for longer life, keeping family size. And in the 80s now, they give up communist planning and they go for market economy, and it moves faster even in social life. And today we have in Vietnam the same life expectancy and the same family size here in Vietnam 2003 as in the United States 1974 by the end of the war. I think we all, if we don't look in the data.
I'm going to stop it at that point. The point here is, imagine how many tables or how much data we would have to look at in order to see what we saw demonstrated here graphically. So one of the focuses of this course is using statistics to summarize data, means, standard deviations, so on and so forth, but also using graphics to help us understand how data is organized. Let me get rid of this and go back. Meeting. Is that my screen? Yeah, that's my screen. Watch this. With the right one. Oh, it's up here. There we go. So Angela, we kind of lost you in the process here, I think. Were you able to watch that on your own computer? Okay, good, excellent. All right, so let me move on from here. So let's actually get into a little bit of practice now. If you go onto your computers, you can log onto Blackboard. Both of you guys can log onto Blackboard now. You can't log onto. Oh, you can't get on. Why not? Passwords or something like that. Let me get you on. I think mine will work. Okay, do you know your password? You wait for that one. I'll try this one. Okay, what I was going to, hey, Angela, you too, if you can hear me. What I was going to suggest you do is go onto Blackboard, and there are a series of little data files on here, numbered 1 through 8. Right-click on each one of them and save it to the desktop. So you have it on your desktop to work with. And we're going to go through with those exercises. Did it come up? Your machine's slow also.
No, mine's working.
It's just like me. Oh, you're on. Okay. Let's go to Blackboard. Go to the last side. Okay. Let's go to Sessions. And the June 4th session. Okay. And each one of these. Yep. Each one of these. Each one is right click on it, say save as, and then save it to the desktop. Save target as or save as. Okay, click on desktop. Good. And that's it. Save. Good. For each one of those, we're going to work with those files. Okay, and that goes for you too, Angela. If you would download those 8 files that are numbered 1 through 8 inside the June 4th folder. If You guys can follow me as I work on it as well. I've already downloaded them. They're here somewhere. Yeah, matter of fact, let me move them over so I got them in one spot.
I can't open number 6.
Okay, what is number 6? That's an R file. You don't have R installed on here, probably.
Oh.
That's okay. Don't worry about that one. We'll probably skip that one anyway. I'm going to open number 1, for starters. I'll give you a chance to catch up. Okay, so I'm starting really at the basics here because I really don't know how much experience. We have students that come in here and have worked with every other form of software in the world, but they've never worked with Spreadsheet. So I kind of I'm going to spend just a few minutes on the very most basic parts of this so that hopefully not to bore you to death, but there may be a student or two out there that really, would benefit from a little bit of understanding of this before we move on. Good. Then there's 2 then that'll benefit from it. By the way, while I'm waiting for you, pay attention to getting online with this stuff and getting started up. But you guys have taken statistics before as undergraduates?
Yeah,
Okay, long time.
A long time.
Okay, good. I like to hear that. Good. One of these days when we have a little bit of extra time, I'll play you a video online that from a comedian from the 70s, Antonio Novella. Antonio, and I think it's a very similar name to the woman that used to be the Surgeon General. Novella is the last name. But at any rate, he played this character called Father Guido Sarducci. And he was, come in with a hat and dressed as a monk and so on and so forth. And he did a lot of shtick. And one of them was he was talking about starting his own university. The only thing he was going to call it the 10-minute university, right? Because he figures he can teach you in 10 minutes anything you remember 5 years after you get out of college. So, you take a language, como está usted. That's all you're going to remember in Spanish anyway. So this is why we learn the rest. Just learn that. And so on and so forth. And he has you take economics, supply, and demand. 5 years after you take an basic economics course, all you remember is supply and demand. Why bother with the rest? So anyway, he goes through this whole thing. But it's the same kind of thing here. I know you guys taken statistics before, but I know if you don't use it in practice, you remember very little of it. But hopefully some of it will come back. Okay, so at any rate, the basics here is, I'm going to blow this up a little bit, make it easier to see. Basics here is when we work with a spreadsheet program, any spreadsheet program, there were many in the past, Lotus 123, Multiplan, VisiCalc, the one I told you about before, the first one. By the way, one of the reasons why you don't see VisiCalc anymore is they didn't bother to copyright the program when they did it. Their attitude, they were childs of the 60s. Their attitude was that they were doing this to improve the world, and they didn't want to, freeze its development like that. But so at any rate, there's some videos of them talking about that as well that are interesting. So basically, a spreadsheet is a series of cells that you see that are identified by letter for column and by number for row. So for instance, in this particular cell, which is empty, I would identify as B7. Okay, in any of these cells, I can create what's called a label, which is just a name, a word that I might type in there, like January. Or I could put a number in, like number 234, or I can install a function. A function is any kind of operation that calls on it to do a calculation. So, for instance, if I look over here, I have information that's typed into 6 cells. And those 6 cells, one of them is a label. The other 5 are numbers. Next to it, we have another label, unit cost. This is count representing the number of items that were purchased. Unit cost represents the cost of each item, $11.20, for instance, $20, and so on and so forth. Actually, I could go in here and I can actually format those cells. Notice I highlighted them together. I could format those cells and tell it, well, identified it as currencies. It's a little easier for me to see if I want. Okay, so let's say I wanted to figure out how much each of those 10 items, what those 10 items cost me altogether. I can actually go to this cell and create a function. And I do that by first typing in an equal sign. As soon as I type in that equal sign, you see there's a number of changes that go on. If you look over here by this little f of x and this open space here, when I type in an equal sign, that's going to change, right? And a few of these operators up here changed. So it now knows that it's waiting for me to complete this operation. So I'm going to tell it that I want it to multiply 10 times $11.20. I could just do that 10 times 11.2, and it'll do the calculation for me. Use the asterisk to represent multiplication. I could also, instead of just having it do, I can use plus, minus, so on and so forth. Instead of it just having it do the operation directly for me, I could tell it, well, let's do it using information that's in other cells. So for instance, type in an equal sign, and instead of typing in 10, I'm going to tell it, take the value that is in the cell F3 and multiply it by the value that's in F4. And it does the same calculation. Oops, something wrong there. F3 times, G4, yeah, there you go. It helps if I use the alphabet in the right direction, yeah. G4. I'm sorry, G3. And that's what I did. I went down instead of across. $112 does the calculation for me, just as it did before. Now I can continue and say here equals F4 times G4, and it also do that calculation for me as well. Notice the case didn't make a difference. The other thing that I could do is I could click in here, hold down my left button, and drag down. So I've identified this as my starting cell, but I drag down to all these other blue cells. And I can go up here to edit and tell it to fill down. Now, Excel automatically figures that when you have two numbers in columns side by side, and you're doing a calculation on the first one, when you copy it down, you're implying that you want to do the same. You don't want to copy that number 112. You want to repeat the calculation going down. So I'm going to say, go ahead, fill down, and notice how this one is now F5 times G5, F6 times G6, and so on and so forth. It copied that formula down. This is another strength of this, is that you can repeat these calculations very easily. And if I want to get the total, I could say it's equal to H3 plus H4. And so I'm not even going to bother to type in the rest of it. I could do it that way, just add the 5 cells together to get the overall total. But there's actually functions that are built into Excel. One of those functions is called sum, S-U-M, right? And you'll notice that as soon as I typed in the equal sign, S-U-M, I started to see some words appear down here, which are functions that start that way in Excel. And then I'm going to put in the parentheses. And when I put into parentheses, it tells me, well, at this point now, just put in the numbers that you want to take the sum of, right? So I'm going to say I want the sum of H3 to H7. And to say to H7, I'm going to put a colon in and say H7. Close parentheses. And now it adds all of them up. That sum is your first use of a function. Okay? So we've added those together. Another way I could use that equals sum parentheses. Now watch that. Once I have the parentheses, I can go up here, click down, and continue to drag without lifting, and it'll fill in that range of numbers for me. And I'm going to close the parentheses and hit return, and it does the same thing. Now, this is pretty interesting, right? That you can do this kind of thing with it. It looks like it might be useful eventually, and so on and so forth. We found one function that we use. A lot of interesting things we can do with it. Let's go to the next spreadsheet, number 2. Okay, you keeping up with this, Angela? We're going to number 2. Okay, let's look at a practical application to this. And this is one of the strengths of this program when you're using it for financial operations, for for engineering and so on and so forth. Maybe not so much statistics, but certainly for a lot of other applications. Here's somebody's monthly budget. Okay, they spend $40 on their phone, $500 a month on entertainment, rent's $500. Obviously, they don't live in New York, or they're sharing with 12 people. Transportation, tuition. So their total debits, their total spending each month is equal to the sum of all these values, right? And we can calculate that. They're spending $1,700.40 a month. The amount of money that's coming in each month, have a job. I'm gonna sneeze. No, I'm not. Okay. They have a job, make $1,000 a month. A sum, we're going to add that all together. They make an extra $200 tutoring, and mom and pop help out with a couple $100. They're still pretty young. Okay, so they're making $1,400. Obviously, we have a problem, right? Okay, and the problem is that the balance they're making $1,400 minus what they're spending. They're in the red, $340. So they have to make some adjustment here. Now, this is where we get into this what if kind of function in Excel, where you don't have to repeat calculations. Well, let's make some adjustments here. Food, well, maybe we won't go out quite as often to eat. Maybe we can get down to 160 on that. Nowadays, this probably be more like a week, right? How about entertainment? Yeah, well, we won't go to any Broadway shows. We'll stick to movies. Let's knock $200 off of that. Well, look at that. We have a balanced budget now. So notice how it updated all of these values as I made the changes automatically. So in finance, they like that because they can see what is the effect of changing the cost of this item versus how many we sell. How does it affect profit? How does it affect our projections for the years going forward? And in engineering, you can see, well, what if we change the thickness of the titanium to 12 gauge instead of 14 gauge? How does it affect the stresses on the bridge and so on and so forth? So you can use this for a lot of kind of what if situations. And in statistics, if you're doing a collection of data, you can also use it, for instance, so that when you do your statistical analysis, that if there's an error, you find an error in your data that you inputted, you can change it and it'll self-adjust the outputs that you have, the results of your statistical tests. Right, so there's some value to that as well. Let's go on to the next one. Number 3. The other thing that it's very good at is presenting graphical data. I'm cheating here just a little bit. There is a graphics function, charts function, in Excel. Okay, and you can get very sophisticated graphics out of Excel. This data represents a mold sampling in a, say, apartment or something like that, or in an office. Okay, so here's a 5th floor reception, behind reception, conference room, 5th floor hall. Here's 5th floor finance office, 5th floor hall outside the finance office. And here is what our levels were for total mold spore counts per cubic meter outdoors versus these various indoor locations. Okay, so that looks pretty interesting. It looks like this a little higher than there. I mean, can I make any conclusions here? Well, maybe if I look at this graphically, it'd be a little easier to understand. I've organized this data in columns and rows in a manner that's going to help us make it easier for me to create a graph chart or a graph very, very rapidly. So I'm going to highlight the data that I want to present graphically. I'm going to tell it I want to present it as a clustered column chart, a bar chart. And bingo, right there we have a graphic representation of this data. I'm going to get rid of that legend. And so we can see that the 2 indoor locations have similar levels, but they're both lower than the mold spore counts outdoors. Okay, now you guys, nutrition, epidemiology, nutrition. Okay, but you've heard of indoor air quality, right? What would that tell you, that the mold spore counts indoors are lower than they are outdoors? That's a good thing. You would expect that, right? Because mold from outside comes inside, but your air conditioning and the air's not moving, so it settles out. So you would expect the mold spore counts indoors to be lower than they are outdoors. Okay, and then the fact that they're similar in both areas, the reason why they probably check two areas is because probably they're getting complaints in one area, they're not getting complaints in the other, right? So the fact that they're similar in both areas suggests that whatever the complaints are coming from, maybe it's not mold spores, right? The other thing you look at when you do this kind of thing is to see what the predominant species are. We don't see that information here. So if there's a predominant species indoors that you don't find outdoors, you say to yourself, well, if it's outdoors, I find it indoors, not a big surprise. But if it's not outdoors, but I find it in large numbers indoors, maybe it's growing indoors. So you can kind of deduce this. And we do this kind of stuff because nobody has agreed on a standard for what's too much or too little, or which ones are really bad molds and which ones are not so bad molds, and so on and so forth. So we use a comparison. But here's a way that we could translate this kind of staid numerical information into something that visually is easy to see, right? Not quite Hans Rosling caliber, but you get the idea that we can use Excel to do this kind of stuff as well. Okay, now if only we could get Excel to do statistics. Let's open up number 4. Okay, we randomly sample a population of let's see. Let's say that this is blood pressure. The lower one is diastolic blood pressure, right? Yes. Okay. Let's say this is diastolic blood pressure, and this is a random sample of nursing home patients in a facility in the Bronx. There are 1,000 beds in this facility. We randomly sample 10 out of 1,000, and we want to know what the average blood pressure is for the population in this facility. Okay, so another word for average is mean. Mean. Now, is this X bar or is this mu that I'm going to calculate now? Is it X bar or is it mu? What do you think? Mu is the population. X bar is the sample mean. So since we're only going to calculate sample mean, it's going to be X bar, exactly. It's a statistic, not a parameter, right? The only way we know the parameter, mu, is if we sample everybody in that, all 1,000 people in that nursing home. Okay, so let's calculate the mean. There's a few ways I could calculate the mean. One is to add all these together. Oops, sum, parentheses, and I'm going to add all, they're going to click in, drag down, close that, and so on and so forth. Except now I'm going to click in here, I'm going to go up to the top here, and divide by, there's 10 people in the sample, divide by 10. That's my mean. Just add them all together, divide by the number of people in the sample. That's my mean. Well, there's an easier way for me to get to that, and that is equals, okay, and now I want to calculate the mean. Spss Excel does not have a function mean. See, when I hit parentheses, nothing happens. Okay, it does have a function called average. And parentheses, and now you can see that it's waiting for operators, for numbers to go in there. So I'm going to highlight all of these numbers and see if it'll calculate the average for me. And indeed, it gave me the same number as when I did that other operation. Okay, so what about the median? Okay, let's try median. Equals median. And parentheses, and sure enough, there's a function for median. And again, I'll just put these numbers in here. Okay, and the median is a little bit smaller than the mean is. Okay, interesting. Well, as we move forward, we'll learn more about that. How about mode? M-O-D-E, parentheses. What is the mode? What's the mode of a sample? What's that? Most frequent, right? Most common output, most common measurement. Okay, I'm going to highlight that. With numerical variables, you usually don't bother with mode because you could wind up with really kind of bizarre stuff. Because you might, like if it depends on what your data is like. I'm using things rounded to the 5, 75, 80. So I might get a practical mode here, most frequent value. But if we were measuring blood pressure, 79.1, 82.3, you can imagine that it's going to get kind of weird because I might get 2 people with 62.4, but they just happen to be 2 of them, and it could be one of my modes or something like that. So it doesn't make quite as much sense. You got to use it a little bit more carefully. So if I look for the modes, it tells me that the most frequent value happens to be 80. And if you actually go in there, you see it comes up like 3 times, I think, or something like that. Okay, So I have three measures of where the center of this is. In other words, the middle. Okay, three measures of what the average or middle of this sample and this population is. I think the average blood pressure of this population somewhere around 80, 82 and a half, right? Around the mode where the median the mode is, right? So I have an idea where the middle is. The other thing I might be interested in is how spread out are the values. If the middle is 82.5, well, are all the other values, are they all between 80 and 85, or are they between 60 and 100, right? We want to understand how spread out these values are. And one of the ways we can do this is just calculate the minimum and the maximum. Equals minimum is equal to min. There's actually a function called min. I click in there, okay, it'll actually put that parentheses in there for me. And this lowest value happens to be 70, equals max, parentheses. Okay, and I'm going to discuss in a second how do I know these are here, and where can you find them? Okay, and the maximum is 75. In statistics, there's a function that we call range, which is the difference between the maximum and the minimum, which is just going to be 95. Whoops, I didn't put an equal sign here. Equals 95 minus 70. Notice I'm in the habit of not typing the cell numbers and letters in, but instead clicking into them to identify them. And that helps because it makes it less likely you're going to make an error, like a typo, like I did right at the beginning there, where I said instead of going down and across, I went up and so, it's a lot harder to make a mistake when you're actually clicking into the box that you want. Okay, so the range is 25. Okay, so that's an interesting measure of our range. I'm just going to see what the next one is. Okay, so there are other measures of spread that we're interested in as well. One of those measurements of spread is the standard deviation. Another is called variance. Right? And we're going to be interested in playing around with those, but we're going to actually maybe calculate those and see where they come from. I'm actually going to calculate it here using the statistical value, using the function VAR parentheses. The variance is 56.94, it's 57 basically. The standard deviation, surprisingly, is just the square root of the variance. Equals standard deviation, parentheses, and I'll calculate standard deviation for A1 through A10, and that's 7.55. Just to show you that's true, there's a function SQRT, parentheses, the square root. I'm going to have put in the cell E3 and have it calculate square root of that and see it comes out the same as the putting in the standard deviation. So really it's just the square root of that. So these functions help us quite a bit in terms of understanding the sample, the spread of the values, the middle of the values, and so on and so forth. Remember we were talking about box plots before, right? Now, what were the important values that we were interested in as far as a box plot was concerned? We were interested in the minimum value, that we know that to be 70. That's that bottom feather. What's the top value? 95. That's that top feather. Well, how about the beginning of that red box? That's the 25th percentile. Let's see if I can't calculate that. Equals percentile, parentheses, and now it's asking me for the array, the numbers that I'm interested in, the range of numbers I'm interested in, comma, and K represents the percentile, 0.25. And I'm going to hit enter, and the 25th percentile is 80. Right, so I know where to draw the bottom of that box. So what about the 75th percentile, which would be the top of that red box? Right, that's going to be equal to percentile, parentheses, and array is going to be this group of numbers here, comma, 0.75 for the 75th percentile, and that's going to be 88.7. And what about the median? The median is the 50th percentile. And that's going to be that bar in the middle of that red box before, which is going to be the array. Whoops, parentheses, I put it in there already. Comma, 0.5, 50th percentile, middle. Okay, which is 80. Notice that the median and the 50th percentile are the same thing. Okay, 50% of the people are above that, 50% are below that number. Okay, so what have we just done? We've used Excel to perform about 10 or 12 of our most common statistical that describe a sample. Right? Give us an idea what the middle is. Give us an idea what the variability, what the size of it is. Okay, so let's.
Professor?
Yes.
Sorry, before you move on, it's Angela. Do you mind going over the variance and the standard
Oh,
deviation?
I got
one more
something
time?
better. I got something even better for you. I'm about to explain how that's calculated. Now,
Thank you.
I'm the only one in the department that actually does this. And the only reason I do it is because after 10 years of not having taken statistics, everybody knows, everybody vaguely remembers variance and standard deviation. But I challenge you that I'm sure at least half of the people don't remember how it was actually calculated. And it comes up later on because we're going to work with a few values later on in the semester, words and values that come up, like things like sum of squares and so on and so forth, that and degrees of freedom that are important later on that are actually part of all this. Let me see if I have a good way to do this here. Actually, I'm gonna just notice what I'm doing here. I'm highlighting these 10 numbers and I'm gonna say copy these 10 numbers. Okay, you could also just click in here and say copy if you want. And I'm gonna close this. I'm gonna open a new Excel file. When I know I have this somewhere else, but I don't want to at this point stop now and go into. I'm going to take a break after we do this spreadsheet. So if I can just impose on you to stay awake just a little bit longer. It's late, and I know keeping an eye on this stuff or listening to this stuff can get a little tedious after a while. Okay, so these are all the values. These are my X's here, right? I just copied them from somewhere else. I'm gonna center these things so a little bit more convenient. Okay, these are all my values here, my 10 values. Okay, so now I'm gonna calculate my average. Whoops. I'm gonna call it the mean. Okay, my mean is equal to average, parentheses, and I'm gonna find the mean of all these values here. My mean is 82.5. Okay, we're going to invent a number that describes the variability of these values from the mean. How different are all these values from the mean? We're going to invent our own. Okay, and the way I'm going to do that is I'm going to say, well, in order to do that, why don't I just take the mean, X bar, and subtract each value from it? How's that? Right? I'm going to do that right now. Equals. So this cell here is going to be equal to 85 minus 82.5. Okay, and it comes out to 2.5. 85 minus 82.5, 2.5, right? Makes sense. Okay, and then I'm going to do this. Instead of doing that, I want to copy this function down. I'm going to drag it down, and what happened here? Something went wrong here, didn't it? Okay, what went wrong here is that instead of calculating A4 minus, here it was A3 minus B14, I wanted to continue to subtract the 84 from each one of these values, right? But what happens is, remember Excel, and the next one it's going to go step down, A4 through B15, which is an empty cell here, A5 through B minus A16, which is an empty cell, right? It kept moving both cells down, which doesn't work. It needs to keep using the 82.5 for each one of these. There's a trick here. Instead of telling it to subtract in this first cell B14, put a $sign in front of the B and a $sign in front of the 14. Okay, that doesn't change the calculation here. But when I go to copy it down, it freezes the B14, but continues to go down in the A column. Right? So see, even down here, it's A10 minus B14. That's called absolute addressing. Usually Excel uses relative addressing. When you copy stuff down, it copies everything down with it, all the formulas down with it. That does absolute addressing. If I confused you there, what I'm going to do is instead, I'm going to type in 82.5 because at this stage, It's nice that you know that, but I don't want to confuse you right now. I'm just going to say, I'm just going to call this column X bar. And I'm going to copy that 82.5 down. It's just a number and I'm copying it down now. I typed it in. Okay, so now X bar minus X, the difference between the mean minus X, difference between the mean and each value is equal to 85 minus 82.5. And then I can copy that down and the formula will advance and I'll get the differences for each one of these. Well, okay, so now if I have a lot of variability, these values are very different from the mean. When I add them up, I'll get a big number, right? So I'm going to add them up. Equals the sum of all these numbers. And what do I get? I get 0. Definition of the mean. Half of them are above, half of them, it's the arithmetic average. They're going to cancel out. Positive sign and negative sign canceled out. I can't just add up the differences to get a measure of how variable each value is from the mean, right? So I need to do something to make these positive numbers. So what can I do to X bar minus X to make it always a positive number? How about multiplying it by itself? So I just take X bar minus X and I square it, right? See what happens here. Equals this times itself. I'm going to add these together. I'm going to copy this down. And now I'm going to take the sum of that. And there's a big number. I got number 512. So you can see that the bigger the differences are, the bigger the square of the differences are, and the bigger this number, which is the sum of the squares of the differences. Sum of squares. Right? It's the sum of the squares of the differences. So this number represents the variability between the mean and each individual value all added together. Right? There's a problem with that number. And the first problem with it is it represents the total sum of squares. I want to know what the average difference is. So the average difference, in order to figure that out, I'm going to take the total sum of squares and divide it by 10, the number of values there, right? Okay, 51.25 is the number I get. I just lied to you. In statistics, instead of dividing the sum of squares by 10, we divide it by 9. We divide it by something called the degrees of freedom. What do we mean by degrees of freedom? In its simplest form, you can think of it, you might be able to think of it this way. If I have one number, and how many choices do I have in numbers? I have no choice. I just have that one number. If I have two numbers, I have one choice between those two numbers. If I have 10 numbers, I have nine choices that I can make. So the degrees of freedom basically is the number of degrees of freedom in choosing these numbers. So what I've done here is I've taken the sum of squares and divided by the sample size minus 1, or in other words, the degrees of freedom. We have a name for that. That's called the variance. Okay, and again, the variance now is really kind of an average of the sum of squares. Just that I happen to divide by 9 instead of 10, right? So the variance gives us the more variability there is between individual values in the mean, the bigger the variance is going to be, right? So the only problem with the variance is a whacked out number relative to the real differences. Why is it whacked out? It's whacked out because we squared these values to eliminate those positive values. So now, instead of leaving it like that, I'm going to bring it back into the realm or the order of magnitude of the original numbers, the original differences. I'm going to do that by just taking its square root. And the square root of the variance is 7.54. You remember what I called the square root of the variance before? What did I call that again? The standard deviation. Okay, I'm gonna get that to display that way. It's called the standard deviation. That's where these terms come from. Variance and standard deviation. They come from this calculation. I mean, you could have sat down and invented this yourself if you wanted to, right? It's not really not that complicated. The idea here is that these are measures of the variability of the individual values away from the mean. Okay, and basically it's an average of the differences, especially standard deviation. When we move forward, when we start to move into some of this stuff, we're going to live and die on this idea of standard deviation. This is really one of the most important concepts that we're going to learn in terms of how we're going to apply statistics. This is a measure of variability that we're going to apply to normal distributions. Don't worry about that for now, that word for now, but it'll give us a chance to go forward and figure out how we're going to estimate the variability of these values and how that variability tells us information about how reliable our sample is. Imagine this. Imagine that you took 10 samples and you came up with numbers like 87, 88, 87, 86, 87, 88, and so on and so forth. And you found the average, and you said the average is 86 and a half. You have a lot of confidence that that's pretty much what the population mean is going to be, right? But now what if you got the same average, 86 and a half, but the values you measured were 92, 65, 110. See all the variability in there, individual value? The mean might be the same, but it's so variable. Now you're not as confident that that mean really represents a true mean of the population, for your particular sample. Just because the numbers are so variable. It would have been so easy for you to pick 10 numbers that are higher than the mean or lower than the mean, and so on, because they're so variable, right? So that's standard deviation. That's an important concept to this. So you could do this if you like to torture yourself, or you could just simply say STDEV. DEV, parentheses, see standard deviation, and then highlight the 10, and then select the 10 numbers and get the same thing without going through all that calculation. But that's where that number comes from for that function. Does that help, Angela? Angelia, excuse me. Angelia, does that help? Good. A capital yes, I like that. Excellent. Okay, how about you guys? You okay with that?
So like for a test, we would have to know all of that.
Is that bad? That for a test you would, there's a homework where you do this. But on a test, I wouldn't bother to make you go just because it kills too much time. I would expect you to use the functions instead of that. Okay, now, how the hell do I know all these things exist? If you go up to this little f of x, now I'm using Excel on a Mac. This is also a 2010 version or something like that. If you see it on a PC, it uses ribbons, but it looks a little different. But they really kind of basically look the same. If I click on that little f of x or function of x or formula builder, a window comes up where you can search through all the different kinds of, like right now, it's the most recently used ones, right? You could also see them, database, all the functions that are engineering functions, all the functions that are, what are these? Information functions, IT functions, reference functions, sine, cosine, you name it. And look, there's a second section here of statistical functions, average, right? Chi-square, counts. Oh yeah, count. Here's a simple one. Equals count. Oops, excuse me. If I forgot to tell you, if you click on it here, it'll come up where you can fill in boxes in order to tell it where the data is. In other words, between here and somewhere else, right? Instead of doing it the way I was doing it, where I hit an equal sign and type in the value, hit parentheses, and then wait for it to tell me what to do, and then highlight these. It actually counts them for you. It tells me that there's 10 values there, right? And in fact, I think if I eliminate one, there, now it's 9 values. Right? So it actually will count them for you as well. But you can go through this and you can see all these different functions. And if you click into it, for instance, if I go to chi-square, right, I can click in here and get some help on how to use this function and what this function means and so on and so forth. Right? But as we go on, you'll see me using these various functions. So you might kind of want to catalog them for yourself. I'm actually, tell you the truth, I think somewhere I can post it. I'm sure in previous semester I've put together a Excel sheet with a list of the most commonly used statistical functions in Excel, and what numbers you put into them and what that gives you when you come out of them, and so on. So I'm sure I can dig something up, but you might want to create your own as well. Okay, so that's where I find these things. That's where we would find these things if I need them. Now, yeah, so I could also, for these numbers, I could go back and I could do minimum and maximum to calculate the range. I could do the median function and so on and so forth. A little tedious, but here's a mechanism for doing this that doesn't involve, using a crank or pencil and paper and so on and so forth. That does it reasonably quickly. On the other hand, there may be a more efficient way to do this, right? That's what we're going to segue into SPSS. But I think before we do that, let's take a 10-minute break.